Hi, my name is Lincoln Kong. I will present our work on software-hardware co-design for the matching of regular patterns. In this talk, I will first introduce some background on the matching of regular patterns with counting. Then, I will show our software design that provides a static analysis of regular patterns. Finally, our another presenter, Qi Xuan, will show our hardware design. Regular patterns can be described with many formalisms, such as regular expressions and finite state automata like DFAs or NFAs. In our work, we are particularly interested in the pattern matching with regular expressions, which we abbreviate as regex matching. This is because it is widely used in many real-world applications. For example, in text processing, we can use regexes to describe text patterns and detect them in the input file. In bioinformatics applications, we can encode protein patterns as regexes to match certain protein sequences in a dataset. Moreover, regex matching is broadly used in network security applications. Classical regexes involve operators for concatenation, alternation, and cleaning star. They can be translated into NFAs whose size is linear in the size of the regex. In practice, regexes have other useful features, and counting is one of these features. Here, the highlighted part means the subpattern R is repeated from M to N times. Counting makes regexes more succinct. For example, we can write a complex regex into an equivalent but shorter version using counting. Counting is frequently used in real-world regexes. We have considered 5 real-world datasets, and in each of them, there are a large number of regexes that have counting. Many techniques have been developed for regex matching, and many of them are based on the execution of DFAs or NFAs. Compared to DFA, NFA-based techniques are memory efficient but relatively slow. The inherent parallelism of the hardware provides opportunities to parallelize the execution of NFAs, which give both memory and time efficiency. There are several kinds of hardware that can be used for regex matching. From CPU to GPU to FPGA and to ASIC specialized for regex matching, throughput has increased from megabytes per second to over 2 gigabytes per second. Yet the energy cost dropped by orders of magnitude. However, prior hardware-based approaches do not adequately address the memory-efficient treatment of counting in real-world regexes. To handle regex with counting on hardware, the naive approach is to unfold the regex and use the unfolded regex to perform matching. However, unfolding can be expensive when the upper bound of the counting is large. For example, for regex R repeated n times, unfolding can lead to an NFA of size linear in n or DFA of size exponential in n. Naturally, a simple solution is to use a counter register to record the counting information. To illustrate, instead of having an NFA of n+1 states, we can insert a counter to state 2 that counts the number of letter A's. And we can report a match when the value of the counter goes to n. By doing this, we record all counting-related information but use much less memory. However, there's another case of counting that is more difficult to handle. Let's consider a regex that describes the pattern that, for an input sequence from right to left, the n+1 symbol is A. In this example, state 2 may have multiple counter values for an input sequence. So a single counter is not enough to hold all these values. Therefore, another challenge is that there are different cases of counting inside the regexes. The easy one only requires a counter register, but the difficult case needs more memory. To efficiently handle the matching of regexes with counting, in our work, we have created software to provide static analysis over regexes. Based on our result of analysis, we have augmented a state-of-the-art ASIC accelerator by adding special modules to handle counting. Our design has two key features. We provide a compiler that distinguishes between the easy and difficult cases of counting and allows users to easily transform regexes into hardware-readable programs. Also, we provide a hardware design that is as fast as the state-of-the-art hardware accelerator, yet uses less memory and energy. Now let's talk about our software design. As an overview, we provide a static analysis over regexes. And we have implemented a compiler that generates a hardware configuration file based on the result of the static analysis. To perform the static analysis, we first transform regexes into non-deterministic counter automata, which we abbreviate as NCA. NCA is an extension of NFA with counter registers. We choose NCA because it provides an abstraction for naturally describing counting, and it can be exponentially more succinct than NFA. Here, we explain the definition of NCA using an example, which is regex A repeated 1,000 times. First of all, an NCA has a finite set of states, and each state may have a counter register. Then, NCA uses initialization functions to initialize counters. Also, NCA has finalization predicates. Here, when counter X has a value 1000, NCA reports a match. So state 2 can be viewed as a final state. Finally, an NCA has transitions that involve a predicate over the input element, a guard of counter values, and an updating function of the counter. In NCA, a counter value is updated only when both predicate and guard are satisfied. As we have discussed earlier, there are many state-of-the-art hardware designs that handle regex matching by parallelizing the NFA execution. Compared to NFA, parallelizing the NCA execution on hardware allows us to further reduce the memory cost. For example, to support the NFA execution of the regex A repeated 1,000 times, the hardware design needs memory to store 1,000 NFA states. For those state-of-the-art hardware designs that try to store each state with minimum memory cost, they still need at least 16,000 bits of memory. However, by parallelizing the NCA execution, we can use 10 bits to store all counting-related information instead of 1,000 NFA states. Therefore, we can save a lot of memory on hardware. However, as we discussed before, there are difficult cases where a single counter cannot record all counting-related information. To see this more clearly, let's now see another example. We consider an input that is a sequence of letter A's. To begin with, state 1 is active. With the first input, both state 1 and 2 are active. Then, the counter value in state 3 is set as 1. Then, there are two different counter values inside state 3. One is set by this transition, and another is updated by this transition. And finally, there are 1,000 counter values in state 3. Here, 1,000 satisfies the final predicate. Based on our observation, we propose a definition of counter ambiguity. We say the NCA state 3 is counter ambiguous because it may hold different counter values for an input sequence. However, we still do not need to unfold the regex. Instead, we provide a bit vector solution. Here, as the upper bound of counting is 1,000, we show a bit vector of size 1,000, where each square represents a bit. Each bit from left to right represents the counter value from 1 to 1,000. Now, with the same input, let me show how regex matching works with a bit vector. For the first input, both state 1 and 2 are active. Then, state 3 is active, and the first bit in the bit vector is set as 1. This indicates state 3 has a counter value 1. With the third input, we can shift the bit vector by 1. Now, state 3 has two counter values, which are 1 and 2. Similarly, after the whole input sequence is processed, all bits are set as 1, and a match is detected. Compared with the unfolding solution, our bit vector solution uses 1,000 bit vector instead of 1000 states. We have proved that checking the counter ambiguity of regexes with counting is NP hard. In practice, we provide a conservative static analysis that distinguishes between easy and potentially difficult cases of counting. As the benchmarking result, we find our conservative static analysis takes less than 1 second for most real-world regexes. With static analysis, we know whether an NCA state is counter-ambiguous so that we can assign either a counter or a bit vector to each state. Then, we build a compiler to translate regexes into files that are used to program the hardware. As we have explained our software design, now Qishuan will continue to present our hardware design.
Hello, my name is Qishuan. Let me proceed with the hardware discussion. In this section, I will introduce you to our architecture and provide benchmark results. State-of-the-art in-memory regex matching accelerators like Comma usually have two major components. They are the symbol matcher and the switch network. The symbol matcher can be further broken down into an array of state transition elements, or we call STs. In this example, the automaton matches RICE, RICE, and RIE. The STs are configured with the symbols in each transition, and they individually report match or not. Suppose we are currently in state 3, and the next input symbol is E. Well, C, E, and E both match the input, and they report. The switch network, however, gives information about allowed STs based on the current state. So in this case, C is allowed, but the transition E is not. Well, so the matches are updated with the information that only the C transition is valid. And it is passed on to the switch network. Well, the switch network then determines that the next state is state 4, and the next allowed STE for the next input is going to be the transition E only. Well, in short, in a comma-like regex matching accelerator, the symbol matcher sends matches to the switch network, and the network determines the state and the allowed STEs. With no place to keep counter values, the only programmable way to execute NCAs in this architecture is to unfold. Additional STs are introduced to represent different counter values, in this case, x equals 0, 1, all the way to 1000. This solution is highly inefficient, as those 1001 STs take a large amount of chip area and energy. Well, for that, in our argument comma architecture, we add additional modules to support counting. For the easy and difficult counting cases, we provide the counter and the bit vector modules respectively. I'll introduce them in detail. Consider this generic loop in an NCA. 3 kinds of STs are of interest, and they are all connected to the counter module. The transition entering the loop resets the counter. The looping transition increments the counter, and on reaching the last ST in the loop, the counter module decides if there should be more iterations or the loop is done. How does this module compare with unfolding? In this micro benchmark, when n goes larger, the fixed size 17-bit counter quickly gained advantage over unfolding in its log scale plot. The bit vector module, as of now, supports only single-state loops, which covers a majority of cases in our application benchmark. Let's put them aside, and the ST entering the loop sets the first bit in the vector. The bit vector will shift towards the right if the looping ST matches, or reset if the looping ST does not match. And finally, if the target bit, bit n, in the vector becomes 1, the loop is done. Similar to the counter, in this micro benchmark for the bit vector, as soon as n reaches very small numbers, the bit vector quickly gained advantage in both area and energy. For the final real-world application benchmark, we collected the energy and area cost of each module with circuit implementations. These are took from our prior works, the baseline comma, or new ones for the additional modules. We choose a configuration that has 4 17-bit counters per symbol matcher and 1 bit vector per 2 symbol matchers. The bit vectors have 200 or 2000 bits depending on the application. Well, one can also choose different numbers of the modules and sizes as well. In the benchmark, the augmented comma constantly outperforms baseline comma in terms of energy consumption by up to 76%. With the area, some are wasted because of the unused bits in the fixed-size bit vector modules, but when non-ambiguous counting is present, the augmented comma outperforms baseline comma by up to 58%. In conclusion, our work formalizes counting ambiguity on NCA. Also, we provide a compiler that distinguishes different cases of counting. Finally, we extend a state-of-the-art hardware accelerator to achieve energy and area reduction in regex matching tasks with counting. Thank you. We're happy to take any questions.
So in this type of work, I was curious if you think that this type of approach would work relatively well and scale towards other types of automata, like push-down automata to express more complex grammars, or even data-dependent grammars, or to what extent this technique works specifically for kind of regular languages.
First of all, I want to briefly repeat the question. I think the question is about whether we can extend our technique on other automata to, like, say, improve the memory efficiency of the hardware. So I think the answer is yes, because we provide a novel way to handle the counting inside the regular expression. And the counting is basically a syntax feature to explain like the regular expression more succinctly. And I think if other regular expressions can also have this syntax, and this goes to the and it can be built to some like push-down automata or etc. And we can add the corresponding modules like counter and bit vector onto the automata, and we can still reduce the memory usage.
Have you, independently of kind of the hardware aspect, this counting automata seems quite interesting, and I wondered if you gave any thought to, I guess, like seeing its interaction with things like regular expression derivatives or other types of formalisms for defining languages of regular expressions.
So if I understand correctly, you mean like whether we can provide like some like optimizations for other features similar to counting inside the regular expression? It's
yes, exactly.
Else?
Like basically the interaction with between derivatives and I guess regular expressions with counting rather than kind of the unfolded versions.
So if it's related to counting, I guess the answer is yes. And like the unfolding is the naive solution to handle like the regular expression with multiple repetitions. And if we have if we see something that has something similar to counting, that is basically like try to explain a repeated pattern for several times, and then we can also use the same technique to provide the optimization. But for other like more interesting features, I think there's still a lot of room for us to do the exploration.
Okay, it seems like there's no other questions in the Slack thread, and we are at 11 o'clock. So thank you so much to the speakers for this amazing paper, and I guess I'll see you all in other sessions.